Um, okay, so now that we've sort of established some of the language and the way that the data is laid out for analysis of variance two-way, let's go back to this example here with the sap production of trees that produce maple, right? So maple trees. And let's think about what the question of Way ANOVA is. Remember that Way ANOVA is about assessing the equality of means. And so, if you kind of read through this example again, you can see that there's really kind of two different questions, two different main questions. And these questions are referred to as sort of the questions about the main effects, right? The questions about the main effects. We've got two explanatory variables, so there are really two questions. Does the fertilizer or the level, right, or the type of fertilizer affect the amount of sap produced? And the second question is, does the climate zone affect the amount of sap produced? So those are the two big questions that we generally want to ask when we have these types of experiments or studies done. And we're looking for the equality of means, but when we have essentially a crossover of two different explanatory variables, and you might think to yourself, oh, okay, well, just start with looking at the different fertilizer levels. So take this sample of low fertilizer levels, this sample of medium fertilizer levels, and this sample of high fertilizer levels, right? So take those three samples, call it X bar low, X bar medium, X bar high. And eventually, those numbers are measured and looked at specifically, and that will help you understand if there's a fertilizer effect, right? If based on these sample means are then the population means for all the maple trees going to be the same. You could do the same though for the each climate zone, right? You could separate it into 9 trees in each climate zone and do a similar thing. But there's a problem with separating this data. Okay, there's a problem with separating this data. And the problem with separating this data is defined here, and it's what we call the interaction effect. There are good reasons why experiments and statistical studies are set up this way, to look at two variables or to study two explanatory variables at one time. Again, there's lots of reasons why we would do that, but when we do that, we sort of limit ourselves from separating the factors, potentially because of what's referred to as an interaction effect. And it's this question of what if the combination of fertilizer level and climate zone, what if they're affecting one another, right? What if low fertilizer is behaving differently across the three zones? Right? And what if it's behaving differently across the three zones in a very different way that the high fertilizer is acting across across the three zones, right? That's called the interaction effect. If the level of each factor is sort of producing means in different ways across the levels of the other factor, then we have an interaction effect, and we really should not, right? So if there's a significant interaction between the factors, the levels of the two different factors, then we really shouldn't separate them. Then we really need to kind of just look at this as a whole instead of separating the two factors out separately. And so when we look at an example like this, before we get to that, the first thing we want to do is we want to do some kind of statistical test to determine if there's an interaction effect. In other words, there's some kind of interaction between, in this example, fertilizer level and climate zone that really would stop us from separating those two factors. If there's not, right? If the statistics tells us that there's not an interaction between those two variables, what that means is that then it's okay to separate out the two factors, and we do in fact get essentially two new hypothesis tests, one for each factor. So in this example, the question of does the level of fertilizer affect the amount of sap produced essentially boils down to, would the mean sap production be the same at all fertilizer levels? So we would have a null hypothesis that the mean sap production at the low fertilizer is equal to the mean sap production of the medium fertilizer trees is equal to the mean for all trees treated with high fertilizer. Notice it's basically what a hypothesis, null hypothesis would look like in a one-way ANOVA. And then the alternative hypothesis would be that the mean sap production is different at each, or at, I'm sorry, not each, at least at, or let's say for, don't want to use at. The mean soap production is different for at least one fertilizer level. So that would be the hypothesis test for checking whether or not there's a fertilizer effect, okay? And then to determine if there's a climate zone effect, the null hypothesis would be that the mean for the mean sap production for trees in the south is equal to the mean sap production for trees in the central, which is equal to the mean sap production for trees in the north, against the alternative hypothesis that the mean sap level, or the mean sap production, is different for, or in, at least one climate zone. So we end up really with 3 hypothesis tests here. 3, 1 for interaction that we do first, 2 for the row factor, and the third one for the column factor. So in general, in a two-way ANOVA, we have almost sort of 3 different hypothesis tests. Now, you'll notice that these are not written in terms of means, even though that's what ANOVA is for, testing equality of means. They're not written that way because to write them in general, how many means do you have, right? It becomes complicated. So we always start with the interaction test. Null hypothesis says that there is no interaction. The alternative is that there is an interaction. We always start with that. So if we reject the null hypothesis here, if the null hypothesis of no interaction is rejected, then we do not go to the hypothesis test involving the main factors, right? These are the main factors. Because in essence, the presence of an interaction between the factors is, here on the slide it says clouding the interpretation of the main effects. I might use the word confounding. That may be a more familiar word to you, right? It makes it hard to separate or really determine whether or not each factor has an effect on the response separately. But if we fail to reject the null hypothesis, doesn't mean there's absolutely no interaction, but it does indicate that that we don't have evidence that there is. So we'll go ahead and we'll do the test for the 2 main effects. And again, this is equality of means across the levels of both factor A and factor B, right? The row factor and the column factor. So the null hypothesis of no effect would mean that the means are equal, and that there is an effect would tell you that at least one mean is different. Okay, and that's the same for the test of both main effects. So overall, just to kind of put this in the context of the structure of every hypothesis test, you're always going to start with stating your hypotheses. That's what I just described on the last couple of slides. Then you're going to look at your conditions, and we'll get back to that later. Okay. Just like conditions for one-way ANOVA, conditions for two-way ANOVA are a little complicated, so we'll save that for later. Then we're going to have to calculate a test statistic and a p-value. The test statistic is referred to as an F statistic because the p-value is from what's called an F distribution, same as one-way ANOVA. It's a right-tailed test. It's a right-skewed distribution. It has two different degrees of freedom that determine its exact shape, and those degrees of freedom are based on the overall sample sizes and the number of factors of each factor. So there's three different tests, right? So three different tests. So there are three different test statistics and three different p-values. But when you carry out an ANOVA analysis with statistical technology, it's all going to come out in one ANOVA table, right? Remember, an ANOVA table from one way, a two-way ANOVA table is going to just have more stuff in it. Remember to always look at the interaction test first, and if we do not reject, then we can look at the results for the other test. So once we get our test statistics and our p-values, then our decision rule is always the same. If the p-value is less than alpha, we reject the null hypothesis and conclude that there is a significant effect of the factor on the response. If the p-value is not less than alpha, we do not reject the null hypothesis, and therefore there is no evidence of a significant effect of the factor. Right? So that's the general structure of a ANOVA hypothesis test.